So on the drill press, and we're gonna watch a few videos in a few minutes here. But on this drill press here, you'll notice like kind of the main parts here. You've got your base, you've got your column. That column is going to sit perpendicular to your base. If it doesn't, it's useless to us, right? Because on the top of that column is the head, right? The motor, which is inside that drilling head. The spindle has got to be parallel to the column. So if the column is not perpendicular to the base, then the spindle won't be perpendicular to the base, and then we're into a whole bunch of garbage. Okay, so the spindle needs to run parallel to the column and perpendicular to the base. That's really important when it comes to drilling straight holes, you can imagine, right? You also see on here, there's an arrow pointing to a depth stop. This is a really useful tool on the drill press, because what that does is it allows us to set a depth and not go beyond it. So we just drill, and then when it stops and won't go anymore, we're at our depth. So that's a really useful part of the drill press, especially if we have to cut multiple holes. Or if we have to cut a hole that there's a call out on a print that says that the drilled hole to maybe the tip of the drill or to the shoulder of the drill needs to be 0.500 inches deep. Well, if you got a 3 decimal place tolerance and you've only got a drill press to use, you have to make sure that when you're done drilling that hole, it is 1/2 inch exactly. So you can set that depth stop to stop at 0.500 inches. So that's a great little handy thing to have on your drill press. You have your main feed lever. So that's the handle you're going to pull down to go to depth. Now you can imagine if the table was slid down that column a little bit more, and you're pulling that handle and you're not at the bottom of the hole, well, how do you keep pulling the handle? If it only had one handle, now you got to hold it, get your hand up top, and then you got to push it. And you got to stand on the side, you got to turn your hand over, and then you got to lift it, and then you got to grab it again and pull it, right? So that's why you got the 3 handles there. You pull, the next one's coming around, you pull, and then you go to your final depth, right? And then you back it off. So that's why you see those 3 handles on the hand feed lever. The table, you'll see on the back of the table is a table clamp. So that table clamp does exactly what it says, right? You lock that, and that table will not go down or up the column. Now, a lot of these drill presses, they have a track, a toothed track. I don't want to call it a gear, but it's a track with teeth in it, but there is a gear in the table. And as you crank that handle, that rolling gear will pull the table up or it will roll it down. Not all drill presses have it. A lot of them you just have to unlock it, and then you've got to kind of shimmy it up the column and back down. It's not designed to be precise. It's just designed to get your work closer to or further away. That handle and the depth stop are what's going to help you get your precision, right? A lot of times on these drill presses, the table, you can tilt it to the left or to the right, and some of the tables even swivel, which is really, really helpful when you're trying to do 3 or 4 holes and you've put say you've clamped a vise to the table, and you don't want to unclamp the vise every time you got to drill another hole. So some of these tables have some maneuverability to them so that you can just kind of rotate into the next position. And on some of these drill presses, you can also rotate the head around so that you can kind of bring it into another position. You can take that table and you can swivel it right around 360 degrees, so you can get it right out of your way, and you can put a large piece of material on the floor and drill down into that. So pretty universal, very useful. But the drill press, guys, is not the go-to choice for precision hole manufacturing. Now, can you accomplish some precision holes in it? For sure you can. And there's different ways of doing that. But if you want repeatability, you want speed, you want accuracy, working from a datum, a starting position, you're going to do all your drilling on a mill. But the drill press is for less precise, let's say, hole creation or feature creation on holes. What what functions can a drill press perform? What features can it create? So here's the main features, guys. One, we all know drilling, right? That's its primary ability, is to drill holes, to create holes. Two, countersinking. Okay, we'll talk about each of these in a minute. Three, tapping. Four, spot facing. Okay, and I guess it'd be very, very helpful to you if I turn that off, eh? 5, okay, is counter boring. Okay, 6, this does not like me, is reaming. And 7 is boring. Okay, I'll try a different marker. Okay, so here's your 7 main functions: drilling, countersinking, tapping, spot facing, counter boring, reaming, and boring. Okay, so let me tell you what each of these features looks like. So first of all, drilling, let's say these are kind of the description, okay, of each of these features. So drilling is the operation of producing a hole by removing metal from a solid piece of material. Okay, that's in a nutshell. Okay, so drilling is the operation of producing a hole by removing metal from a solid piece of material. So if you're not able to take notes, come back to this section in the video when it's posted to get these descriptions. Countersinking is the operation of producing a tapered enlargement on the end of a hole. So once I've produced a hole here, I can produce a conical or tapered feature on the top of an existing hole. So originally the hole was just straight like this, right? Drilled straight, and then I put a countersink tool in, and that countersink tool came in and it produced, and the tool would continue in here like this, right? And then it would come up like this if this were the countersink tool, and then it would look like that. So that would be what a countersink tool looks like. It looks like a drill, but it has a form that just cuts a conical shape on the top of a hole. Okay, so that's a countersink. Why would we put a countersink hole on the top of a hole? Well, a couple of reasons. One reason is a lot of guys just do it for aesthetics, to remove sharp burrs from the top of a hole. And other times we put it on to allow for a machine head bolt, right? Machine head bolts are a tapered bolt. So that you could create a countersink around the top of the hole to a depth allowing for a machine bolt to sit and stay just shallow of the top of the workpiece. Okay. What about reaming? What is reaming? Well, reaming is the operation of sizing and producing a smooth round hole from a previously drilled hole. So this is interesting. If I want to drill a hole according to a print, the print says this hole needs to be 0.500 inches in diameter. So one of the things we're going to learn in this course, guys, is that precision matters. If you said to me, Jim, you said to me, hey Adam, I need a 1/2 inch hole. I say like just a 1/2 inch. What's the precision? Oh no, I just need a 1/2 inch hole. Okay, so I go over, I'll center drill, and then I'll drill a 1/2 inch hole. I'll take a 1/2 inch drill and I'll just bang it through, right? Is it gonna measure a 1/2 inch? No, right? It'll be a couple of thou, big or small. A drill is not super precise. It's approximate, it's very, very close. But as a drill wears, obviously, you know, the hole's going to get smaller. Or as you grind a drill and it gets shorter and shorter, the hole's going to get a little bit bigger because it's a little wider as it approaches the solid meat of that material closer to the top of the drill shank. So if Jim, you came to me and say, hey Adam, I need a 1/2 hole for this gauge pin. Well, then now I know, well, this hole is, you don't want a 1/2 hole. You want a 0.500 or a 0.50000 hole, right? So what the hole is used for matters, right? And so that is explained to us on the engineered drawing. If you, on your engineered drawing, you just see this and it says, 4 holes, and it just points to the hole and it says 4 times 1/2 inch. Okay, that's what your print says, 4 times 1/2 inch. You know what I'm gonna do? I'm gonna take a 1/2 inch drill and I'm just gonna done, right? Fast as possible. But if this is not what you meant, if what you meant was I need 4 precision holes, I need 4 holes at 0.500 inches, I'm not going to go and just grab a 1/2 inch drill and hope for the best. If I have a brand new, very expensive 1/2 inch drill, I may be able to achieve this to maybe a plus or minus 0.001 or maybe even a 0.0005 tolerance, maybe. But anytime I see a 3 decimal place, and especially if I see a 4 decimal place, I'm going to ream that hole. So what I would do is I would go and I would get a drill that's 1 nominal size smaller than 1/2 inch, right? So I want a drill that, and there's a rule to follow, right? So we'll get to that later, but I want a drill that's approximately 11 to 15 thou smaller than 1/2 inch. I want to intentionally drill that hole a little bit smaller, a certain percentage smaller. And once I've drilled that hole, then I will get a reamer and I will ream that hole to the exact size. And so what a reamer is, it is a precision cutting tool that is designed to enlarge an existing hole. You cannot put a reamer in a drill press on solid material and drill a precision hole. It does not have a cutting point. It only has cutting edges along the length of the tool. So if you try and press that down into a part, you might as well take this marker and try and press it through steel, because there's no cutting edge at all. It just crushes the reamer, right? So you need an existing hole, then you put the reamer in that is the size you want, and then you trace or follow that hole, and it will remove that excess material, create a good finish, and create an exact size. Next, boring. So boring is the operation of truing or enlarging a hole with a single point cutting tool. So again, I'll create a hole to start with, and anytime, guys, that you have to bore a hole to size, cut it as close to size as you can first. If you got to cut a 1 inch 100 thou hole and you have a 750 thou drill, you have a 1 inch drill, take the 1 inch drill, right? Take the bigger drill and get rid of all the material you can, and then put in your boring bar. So and you'll see in your Technology Machine Tools toolbook, it's just a head, right, that fits into your drill press. A boring bar comes out of it, and then there's just a little, it kind of looks like this. So a little tapered shank here goes into a boring head, and then a boring bar will come out, and then your cutting tool will be there, right? Now this is dovetailed here, so I can take the lower half of this boring head and I can move it that way, or I can move it that way. And you'll see my boring bar is off center, right? So I would have an existing hole here, and I could bring the boring head down and dial this out this direction until this cutting tool is just touching this wall. So I'm going to bring this down inside the hole, right? I'm going to bring it down inside the hole with my cutting tool, and just until, as I rotate this by hand, it just starts kissing the inside of that hole. Okay, that's my starting position. Now, if I know that the width of this hole is exactly 1 inch, then, and I need it to be 1.01 inches, 10 thou bigger, then whatever I dial this out in this direction, it's also creating that same depth on the other side because the boring bar spins in a circle. So if I take a cut on this side of 2/1000ths of an inch, 0.002 depth, then I end up cutting 0.004 out of the inside of the hole, right? Because this is a linear move. So whatever I move this, it cuts twice that off the inside diameter. So this is how we bore a hole to size. So I would maybe start with 2 thou, and that should remove 4 thou, and in theory, my new size should be 1.004, right? I should have removed 4/1000ths of an inch. If that's what I get, I know this is cutting accurately, and then I can go and I can try and bring it to size, or maybe I want to take another 2 thou and get it to 1.008, and then take 1 thou on my final cut and bring it to 1.01. So that's how we bore a hole, is we use a boring head with a boring bar with a single point cutting tool, and we engage into an existing hole to open it up to a desired size. Okay. Okay, so that's boring. Okay, spot facing, guys. Spot facing the end of a hole is for the purpose of providing a seat for the head of a socket head cap screw. So we're going to talk about fasteners later, but one of the most common fasteners, actually I probably don't need this up here right now, I could use the space. One of the most common fasteners is something you're probably very familiar with, a socket head cap screw. And inside, if we look down on the top of this, it will have an Allen key driver head, right? So you take an Allen key and you tighten this bolt. This is a socket head cap screw. That's the short form for it, SHCS. It'd be good to remember this because we're going to be, when we talk about engineering drawings, this is one of the common short forms, or common, what do you call that? Can't remember the name. But anyway, it's one of the common short forms so that we don't have to write out socket head cap screw every time, okay? SHCS. So a spot face allows us to take a piece of material that we have a hole in already, and I want to, it's a threaded hole, right? So this is a threaded hole in here, and I want to tighten this bolt down into this hole. But I need a flat surface inside that hole for these corners of this socket head cap screw. I need that to seat down tight and square to my workpiece. So that's what I would use a spot face for. I would create this flat surface, right, to suit the head of a socket head cap screw, just to provide a flat surface. That's it, okay? But if we just jump down one to counterboring is very, very similar to spot facing. The difference is, excuse me. The difference is that a counterbore hole is designed so that the entire head, once I screw this bolt in, the entire head will sit down inside my workpiece here. And this is very, very common in industry, because if I was taking, say this were an upper portion of a die or whatever it is, right? It's an upper portion, it's got to be bolted to a lower portion, and there's no room for clearance up top here, I can't have a bolt head sitting above the part. So we would counter bore the hole so the entire diameter and depth or height of the socket head cap screw will sit down inside once I've screwed it down into the part. Okay. The other thing we can talk about is, or that we want to talk about, is tapping. Well, what is tapping? We probably all know this, but tapping will produce the mating hole for this, right? So if this is my socket head cap screw here, if I need a hole, whoops, I need a hole that, if this is my socket head cap screw head, I need a hole that has a mating thread on the inside right? So that when I screw this in, it has a thread to engage with. So this is the tapped hole. So tapping is the operation of creating the internal thread inside an existing hole. So notice existing is important here, guys. An existing hole is necessary for spot face, counter bore, tapping, boring, reaming, countersinking, right? Drilling creates the hole. All of these other features are created from that existing hole or on that existing hole. So if you're not drilling a hole and you're trying to create one of these other features, stop what you're doing. You need a hole first, right? So just let's remember that.